Attention, please. The session will begin shortly. For the online audience on Zoom channel, I would like to remind you to please turn off your microphone, open the camera, and use the virtual background that we are sharing, and rename your identification to name of participant underscore your affiliation. The registration form will be shared in the last section. Thank you for your cooperation. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Welcome to the general lecture on use of artificial intelligence in weather, climate, and geophysics, a QMUL perspective. We are delighted to have all of you here today. I am Ruth Archana Sihombing, and I will be your master of ceremony for this event. The Honorable Director of Indonesia State College of Meteorology, Climatology, and Geophysics, Associate Dr. Denis Septiadi, MSI. The Honorable, our speaker, Professor and Head Data Science for the Environment and Sustainability, Professor Cedric John. The Honorable, our moderator, Head of Research and Community Service Unit, Dr. Engineering Benjamin Herianto Rusanto, MSI. The Honorable Vice Director of STMKG, Department Chairs and Secretary, Chair of Research and Community, all the Honorable Lecturers of STMKG, and all the beloved participants of today's general lectures. Allow me to read the agenda for today. First, opening. Second, a welcoming remark will be delivered by the Associate Professor and Vice Director for Academic, Mr. Dr. Aris Kristanto, ST MSI. Third will be our main agenda, general lecture, that will be led by the moderator, and the last is closing. Excellencies, participants, ladies and gentlemen, to start this general lecture, we are honored to receive a welcoming remark from the Associate Professor and Vice Director for Academic, Mr. Dr. Aris Kristanto, ST MSI. The floor is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Honorable Professor Cedric John from the Queen Mary University of London. Welcome to Indonesia, welcome to our campus, welcome to STMKG. Respected staff from the Human Resources Development Center of BMKG, Ms. Nina and Ms. Rico. Thank you for coming, and we are grateful for this continued supporting of the collaboration to make the elevated to the education and training in BMKG, especially in STMKG, for increase our collaboration for education and training. And of course, for the all lecturer and all the cadet and all distinguished member of the community academic in STMKG, good morning everybody, good morning everyone. And also in the participant on the Zoom meeting. It's great honor for me as a Vice Director for Academic Affairs, represented for our director, officially in Canberra for assignment, official assignment. So he sent to regard to us in this room and in this Zoom meeting. Today, especially we have Professor John from the QMUL, has become the lecturer today. He's an expert of artificial intelligence in its application in meteorology, climatology, geophysics. And he is a head data science for environmental and sustainability in QMUL. Today's lecture is about the use of artificial intelligence in meteorological, geophysics, and climate. And then I think it's been important for us because the complexities of weather, climate change, and geophysics challenge will be supporting with the AI. The integration of AI offer the groundbreaking opportunities and great challenge for us to make the increasing of the technology. And AI is not only for the enhance our prediction and precaution, but also empower us to develop and more efficient and sustainable solution. STMKG, as educational institution under affiliation of PMKG, play a pivotal role, I think, in the shaping future professional, being meteorologists, climatologists, and geophysics. Today lecturers align perfectly with this mission, providing opportunity for our cadets, our lecturer, to engage with advanced technology that will shape the future of our disciplines. For all the participants, I hope the insights shared by Prof. John is not only in this academic journey, but also inspire to think innovatively and to prepare to contribute national and global challenges. Before we begin, I would like to extend my deepest appreciation to all who involved to make this event possible. And it will make STMK remains being a center of excellence and hub for meaningful academic interaction. Thank you, and I wish you all insightful and inspiring lecturer. Good morning. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Associate Dr. Aries Cristianto, STMSI, for the insightful speech. Excellencies, participants, ladies and gentlemen. Now, we invite the speaker from QMUL to come forward to receive the gifts from us. The gifts will be presented by the Associate Professor and Vice Director for Academic, Mr. Dr. Aries Cristianto, STMSI. Please welcome. To capture the spirits of togetherness, we will continue with a group photo session. We invite all STMKG's Vice Director as well as the lecturers to come us on the stage for a memorable group photo. Please welcome. Thank you very much. Now we kindly invite our honorable speaker, the Vice Director, and lecturers to return to their seats. Please give them a warm round of applause. Before we continue, let's offer our gratitude to Almighty God for His blessings so we could all gather here in a perfect condition. Let's start our general lecture with prayer. I welcome Cadet Muhammad Fajar Al-Ghifari to lead us in prayer.
Assalamualaikum warahmatullahi wabarakatuh. The reading of the prayer will be read according to the teachings of Islam. For those who are religion other than Islam, please adjust according to their respective beliefs. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Hamdan syakirin, hamdan na'imin, hamdan yuafi ni'amahu wa yukafi'u mazidah. Ya Rabbana lakal hamdu kama yanbaghi li jalali wajhikal karimi wa azim sultanik. Allahumma salli ala sayyidina Muhammad salatan tunjina biha min jami'il ahwali wal afat wa taqdilana biha min jami'il hajat wa tutahhiruna biha min jami'i syai'at wa tarfa'una biha indaka a'lad darajat wa tuballighuna biha aqsal ghayat min jami'il khairati fil hayati wa ba'dal mamat innaka ala kulli syai'in qadir. Allahumma ya Allah ya Rabbana. Today we held a public lecture on use of artificial intelligence in climate and geophysics, a QMUL perspective. Make our activities today a useful assembly of knowledge in order to increase our scientific insight, which produce results that are beneficial for the benefit and as a breakthrough for the progress of the nation and the salvation of the world and our hereafter. Ya Allah, give us wealth of knowledge, adorn us with spaciousness, glorify us with piety, and give us health so that we may also be on your path. Ya Allah, Ya Rahman, Ya Rahim, you are the most merciful and the most merciful, so love our parents, our teachers, and our just leaders, who have played so much in shaping us to become better individuals. Give them a reward with the best possible reply for this world and their hereafter. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Cadet Muhammad Fajar Al-Ghifari. Excellencies, participants, ladies and gentlemen, we are now entering the main agenda of today's event, where we will delve into an enlightening general lecture on use of artificial intelligence in weather, climate, and geophysical, a QMUL perspective. Ladies and gentlemen, before we begin the next session, please allow me to introduce our moderator who will guide our discussion today. Our moderator today is Dr. Engineering Benjamin Herianto Rusanto, SSI MSI. The formal education, high school at SMUN 55 Jakarta, Indonesia. Bachelor degree at Physics, University of Indonesia. Master degree at Instrumentation Physics, University of Indonesia, and doctoral degree at TU Brunswick, Germany. The professional experience, Indonesia Meteorological, Climatological, and Geophysical Agency, or BMKG, lecture at Instrumentation Department, Academy of Meteorology, Climatology, and Geophysical, PTB, Germany Working Groups 3.13. And Mr. Benjamin has skill in electrical engineering, instrumentation, metrology, and calibration, laboratory calibration standard, vibration calibration, auditing management system certification, data acquisition system developer, and able to speak and write in English, Germany language A2 certification. Without further ado, let's give these sections to our moderator, Head of Research and Community Service Unit, Dr. Engineering Benjamin Herianto Rusanto, MSI, and our speaker, Head of Data Science for the Environment and Sustainability, Professor Cedric John. Please welcome.
Okay. Good morning, ladies and gentlemen. It is an honor and great pleasure to me welcome you to all today in general lecture. My name is Benjamin, and I will moderating the session. We are also the latest Mr. Aris Cristianto as associate professor and vice director, and all lecture, estimate structural and non-structural official, and the head of study from STMPG. Your support and commitment for fostering academic excellence are truly appreciated. Today lecture addressing a topic of critical importance: use of artificial intelligence in weather, climate, and geophysics. QMUL, Queen Mary University of London, means perspective. Before we proceed, let me pose a few questions to all of you. How can we enhance early warning system for extreme weather event, climate change, earthquake, or even tsunami? What role can advanced technology like artificial intelligence play in solving this challenge? This question underlines why today's lecture is so important, especially for a world facing the impact of climate change and increasing natural disaster. As expert in the field of meteorology, climatology, and geophysics, you, the student, will play a critical role in addressing this challenge in the future. This lecture is designed to inspire and prepare you to innovative where AI can offer solutions. Why Professor Cedric John, you may ask? Professor John is a leading expert from Queen Mary University of London, QMUL, professor and head of data science for the environment and sustainability. His work has revolutionized the way we approach data analysis, prediction model, and mitigation strategy, making him the perfect speaker to guide us through this critical topic. And another question, why it's important to start doing research like this now? With extreme weather, event, and the threat of natural disaster becoming from frequent, there are never been a more urgent time to discuss integrating AI into weather, climate, and geophysical science. This knowledge is essential for building a resilient system and keep life and infrastructure safe. Now, before we start, maybe you can look the curriculum vitae from the Professor John. Is the background of the Professor John is machine learning, neural network, and another, and the biography. He PhD in Potsdam, Germany, and then now 2018 he research in Earth Science, AI, Department of Earth Science and Engineering, Imperial College London. Please give a warm round of applause from him. So, before for another guest, let's do quick together. When I say STMKG, maybe you repeat the Center of Excellence. Okay, ready? STMKG? Okay, thank you. Professor, floor is yours. Thank you. Yeah.
Okay. Salam alaikum, everyone. Good morning. Let's see if I can operate this podium. So either... This is bad. Right. Is that working? Yes? Okay, great. Right, so thank you for the warm welcome. This was absolutely fantastic. It's a pleasure to be here to talk about my research, but also to talk about Queen Mary University of London, of which I belong, and with the BMKG, we have. Thank you very much. We now have an agreement for research and education. So let's see if this works. Probably. Yeah, that's okay. Oh, is this one not working?
Now you can move if you want.
Oh, no, it's okay. I'll stay here. Yeah. Yeah. Great. Okay, so first of all, I want to congratulate you. I've given a lot of talk. This is by far the best flyer ever, okay? and this for two reasons. First, like the graphics, amazing. Second, I am 10 years younger on this photo, so well chosen. So I hope you're not too disappointed. Also, I can see I chose the wrong uniform this morning, right? Okay, this is not my first time in Indonesia, but I haven't been here since 2013. And the last time, I actually went on a holiday to Bali, but I did come to Java just to visit a volcano. Why a volcano? Because I'm a geologist, okay? My background is in earth science. I'm a geologist, and I'm really a multidisciplinary geologist. And so I can see this academy with all the different topics being connected as almost like a home, because multidisciplinarity is so important for meteorology and geophysics. So I did a lot of field geology, notably focusing on carbonates. I also did a lot of geochemistry, so you can see here the multidisciplinarity. And of course, starting in 2015, I started to look really into AI because I've always been interested and I've always done numerical work in addition to all the lab work and the field work. And this is what we're going to be focusing on today, because I think this is the most interesting part of the research for you guys, but also because, frankly, I focus on this since 2017. This has become 100% of my research. So what's the plan for today? So I was given an hour and a half, so you guys are a trapped audience, sorry. And I have really three objectives. First, let's talk about the context. So we have an agreement between QMUL and the BMKG, an MOU that either is signed or about to be signed for research and education. So a big part of my visit here today and tomorrow is to present the school and talk a little bit about why, as either a master's student or a PhD student, you'd want to come to Queen Mary. So I will talk about our master's program, because my understanding is you guys are undergrads, so the MSc would be the natural next step. And I have one slide on the PhD. Tomorrow I will talk more about the PhD with staff of the BMKG who might be interested in this. But the fun bit is the research, isn't it? So my second goal is really to talk about my research, which I will divide into two parts. I will show you how we can use AI for climate research and meteorology or weather prediction. And I will also talk about geophysics, being a geologist myself, and how we can use AI in geophysics. So you can see there's a lot to cover. And mostly what I will do in the research side is show you a lot of things and go relatively shallow. So you don't have to have a deep understanding of AI to understand them. But if you have more questions, please feel free to ask them. So let's start with Queen Mary, right? Why would you want to come to Queen Mary, University of London? Who has heard of QMUL before today? Raise your hands. Who has heard of Oxford, Cambridge, Imperial before? Raise your hands. Two people, okay. Okay, so the point is that we're maybe a bit less known than Imperial, where I used to be, or Cambridge or Oxford. But we are actually excellent. And if you look at, I would say we're the hidden gem of London. If you look at our record, we're 24th in the world for quality of research, 6th in the UK for quality of research. And the UK has a lot of universities, so we're really at the top of the universities here, according to the World University Ranking 2025. If you look at REF, which is a UK-based assessment of research, 92% of our research is of world-class, first-class excellence. So we are a research-intensive university, and that is one of the reasons you might want to come to study with us. We have a global profile. We have actually students coming from all around the world. 42% of our students are international students, so you would find yourself into a very international, vibrant atmosphere. We have a global footprint, so we do have a presence in Kuala Lumpur, not too far from here. We also have a campus in Beijing. We, of course, have our main home is London, but you can see that we have a footprint everywhere. And of course, we're in London. I mean, if you're young, this is an attractive place to be, right? It's a fun place. And we actually are in East London, but we have a lot of different, our campus is basically widespread. We have a main campus, but we have a lot of other campuses. So this is a view on the campus from Mile End, where most of the teaching takes place, looking towards central London. And we're really in East London, and East London is fun because it's vibrant, it's very diverse, and you can see in the background, this is the city of London. You can literally walk to the city. It's about a half-hour walk, or it's a 5 minutes, 6 minutes public transport ride. So you're really in the center of the action. We have, the way the university is divided is into schools. So we have 3 main schools. It's not so important. For you guys, the most important things are really these. So mostly really in science and engineering are where the relevant campuses are, or the relevant departments would be located. And geography, if you do geoscience, is in the humanity and social science. But this is what would be relevant to the BMKG, essentially, remit. The last point is the Digital Environment Research Institute, also known as DERI. And that's important because it's my home, okay? This is where I am. So what is DERI? DERI is a research institute. So I actually moved there about a year ago. I no longer teach. This is a research-only institute. So it's outside of the university structure. We are 5 professors. So you essentially have, what, 20% of DERI here today, okay? And one of our remit, of course, is the environment and sustainability. Which is why I have this very long title. But those of you who would want to come and do a PhD in London, I know this is far in the future for you guys, but you would probably have some form of association with DERI, especially if you do AI, because we are essentially the AI research hub. Okay, so we have several MSc program aligned with the BMKG. An MSc program is a taught master program. It's an intensive 1-year program in the UK. Most UK university, all UK university offer MSCs. At Queen Mary, we've identified 24 different MSc courses that are aligned with the BMKG's objectives, the 4 objectives of the BMKG. So these would be relevant for you if you're looking at doing an MSc at Queen Mary. It's in 9 different departments across the campus, so you can see it's very widespread. One thing I would say is we're very strong on environmental research, on AI and IT teaching. That is really our strength. And we can now look at the different MSCs without going into too much detail. So I have the 4 topics of interest here for you guys. So starting with meteorology. We have some environmental MSCs on water environmental management, for instance. We have a lot of engineering MSCs that would provide relevant skills for meteorology, such as advanced engineering or advanced material science and engineering. Of course, if you're more into math and risk analysis. We also have some very good mathematics there that you could apply to meteorology. And then we have a plethora of AI and data science MSc. Some of them are really fundamental, so if you come from IT and you're a computer scientist, you go to those. But also we have a lot of them that essentially are here for conversion, meaning that you can come with a very different background, not being an expert in AI, and be trained for a year to have the right AI skill to then pursue a career or a PhD. Now, I'm not going to repeat all of them for each of the topic of interest, especially because AI and data science cross-cuts essentially all 4 areas of interest for the BMKG. But we also have some climate-related MSc, so in the environment, the ones that I already mentioned, but you also have, we have a very vibrant bioscience department that looks at conservation and ecology, which has, impact with climate change, and the math and AI is the same. If you're into geophysics, then I would say we're mostly offering MSCs in AI and in math that can then be applied to geophysics. And last but not least, for instrument and ICT, we actually have a lot of engineering MSCs that are of interest to you. So if that's something you're interested in, feel free to contact me and you can actually explore the different MSc that we have for you. So what would be the next step if you were curious about doing an MSc? Well, first of all, check with your supervisor that you're eligible, right, for the funding and everything. I believe you go with LPDP funding. Then check what MSc we offer. Contact the course administrator if you want detail on that particular MSc. And there's a link here that you can visit for inquiries. These are documents that you might need to apply. So transcript of your certificate, you need references, 2 references, statement of purpose, your CV, and a language, an English language certificate. And I know a lot of your peers went to the UK to do MSc, so you'd have a lot of support internally to understand how the process works. This is much further down the line for you guys, but if you wanted to do PhDs, we also have an agreement for a PhD. That's my only slide on this. So we've identified 54 different PhD topics for the BMKG in all 4 teams. It's spread over 33 different individual lead supervisors in 9 different schools, me being one of them, okay? What thing that we want to do is we have a strong desire to co-design the PhD program with the BMKG staff. So the idea would be that you would have 2 supervisors in London, but also a BMKG supervisor, and the program would be from a ground up co-design. So we're sure to ensure maximum return to the BMKG. And you can basically approach people within QMUL. There's an agreement, there's document, there is basically names to talk to them. And if you don't know who to talk to, you can always come to me because I'm the coordinator for this BMKG agreement. Right, so now we go into the topic of today, which is AI applied to basically the environment and sustainability. So my first part is I'm going to show you a few examples of projects we've done on AI applied to climate and weather prediction, and then we'll go into geophysics. But let's start with research part 1, which is AI in climate and weather. So first of all, let's start with the challenge. This is something you guys should be very familiar with. This is a prediction of weather. This is actually over France and Europe. That was back then, I think it was back in August, and you can see that this is the ultimate goal. Produce a nice weather model to be able to predict hourly or even more precisely what the weather is. And of course, you especially are interested in extreme weather events, which can be catastrophic and need to be managed. Now, this comes with some challenges, right? So this is not something that's easy to do. Let me try if this works now. Oh, look at that, okay. First of all, as we all know, it's highly dependent, the error is highly dependent in setting the initial conditions of the model, okay? So that's a problem when you do full physics model, is that the boundary condition of your model are going to impact your prediction. So it's very hard to do long-term predictions because it depends so much on the boundary conditions. So that's challenge one. Because you will basically drift from reality. Okay, so there's ways around this. You can do data assimilation. You can, do the computation more often. So there are ways to go around this, but that's still a challenge. The other problem is we have sparse weather observation, and they're unevenly distributed, and they're not on the grid, whereas all of our models are on the grid. So that's where, again, data assimilation and this kind of approach that I'm sure you're learning in your course are very, very important. But one thing that is really an issue with the full physics model is that they're extremely computationally demanding, right? So typically for European weather station, I think the model is computed every 6 hours because that's how long it takes to compute them. So you don't typically have an hourly update of the full physics model, okay? And it's very hard to do very subgrid or small scale computation. This is why AI is really offering a revolution, or has been, machine learning and AI has been used at least for 10 years in this field, right? And it's a revolution. I'm showing you here one of the latest paper from the Google DeepMind team that actually was published this year on their hybrid model, where they basically suggest to use both full physics and AI models. And why would we want to do this? Well, because AI models essentially allow you to speed up the calculation. Now, by how much, you might ask? By about 1,000 times, okay? So it's much, much, much faster because it's much simpler. It's not as accurate, but because it's faster, you can do more realization. So that's the first thing. The second thing is AI also helps you in weather with more advanced data assimilation. So you can actually take your sparse observation, merge them, and get a better understanding or a better predictability for your weather pattern. Okay. Right, but what is artificial intelligence? So again, let's see a show of hands. Who has studied machine learning and AI? Okay, everybody's, I saw a half hand there. Okay, everybody's too shy. So let's go to the basic. I think we want to explore what artificial intelligence is. And really the goal here is to show you that it's not as complicated as you might think it is. It's actually a series of fairly simple concepts, but then of course you add a lot of simple concepts together and the whole body is daunting at first, right? But I don't want you to be scared of it. So let's start to look at the simple artificial neuron, which is really what fuels the base of all those deep learning models. ChatGPT start with this, okay? So an artificial neuron, you can think of it as an algorithm. This algorithm takes input, okay? So here we have input as x, so we have n inputs, or a random number of inputs. And to each input, we pair a weight. There we go. We pair a weight. A weight is basically a number between 0 and 1 that we multiply the input with, okay? Now, those weights are trainable in machine learning, meaning that we don't know what the weights are. We will train them based on what our data is, our training data is. That's part of the magic of machine learning. Now we have two functions that makes the artificial neuron. The first one is called the transfer function. And the transfer function basically takes the weights, takes the input, multiplies the weights, and add a bias, okay? We do this using linear algebra, so it's in matrix form, but it's a very, very simple thing. You've done that in secondary school. You can see it's a linear function, okay? What's the problem with linear function? What happens if you put 1,000 linear functions together? What do you obtain? A linear function, okay? So linear functions are not good to solve nonlinear problems. That's kind of obvious, and this is why the artificial neuron has a second function known as the activation function, okay? The activation function is a nonlinear function. Now, which function you choose is up to you, but here are two classical ones, the sigmoid function and the ReLU function. And all you need to know about this function, if you look at their response, is that they're nonlinear, okay? So depending on the value coming out of the transfer function, the output at the transfer function will either be 0 or something between 0 and 1, okay? And by adding this, we obtain a nonlinear simple function, right? And if you combine those functions, so if you put 1,000 new artificial neuron, you get a very complex nonlinear function. But the basic is very, very simple. So now we're talking about AI and we think, hey, this is really state of the art. This is cutting edge. Not really. This was published in 1943, okay? This is really old, the artificial neuron. The concept of the artificial neuron mathematically and then electronically dates back from the 40s and the 50s. So what has changed? Why are we now all of a sudden, AI is flavor of the day? Well, a lot of things have changed. First of all, we have more complex architectures, okay? So now we know how to train very deep neural network by a process known as backpropagation that allows us to basically set those weights, those trainable weights, based on the input function. So we can obtain, thanks to this, very, very complex, almost like universal function where we can give complex input, in this case here, an image of a hummingbird, and obtain a classification. So that's the first thing, better algorithm. But that's not really the main thing. The main thing is we have better computation power. In 1943, this was impossible. Now we have really supercomputer, cloud computing. It makes it possible for everyone to basically train neural network. And we have much more data because machine learning AI is all based on data, okay? Right, so now we know what an artificial network is, at least in principle, and hopefully I've convinced you it's not that complicated. So let's look at a few examples of using AI, or example from my research group on using AI for different things of interest. So the first thing is fairly recent. This is from last month. We actually took part on an IEEE competition on essentially predicting weather or improving weather prediction. So what was the idea of this competition? Oh, and we made top 5, okay? So we won the competition, woo! So the principle, this is not always working, so let's go like this. Okay, so the principle of the competition was this. Given the open API, open weather API, so an API that gives you prediction for any places in the world, right? So here I'll show you an example, for instance, where you can see temperatures and relative humidity. Okay, you have 2 curves. It's a 7-day prediction. Can we actually improve on this prediction using any technique you want? So it was completely open competition. You could use deep learning, you could use machine learning, you could use mathematics, you could use voodoo, whatever you want, okay? That was up to you. But the challenge was to predict 6 different variables 7 days ahead, so it was a blind test. You had to submit it with a 7-day prediction at a certain time in 3 different locations. So one in Croatia, one in Bahrain, and one essentially in South Africa. And you can see here the different properties we had to predict. So our solution actually was not to use deep learning. I decided with my team to focus on this problem not as a time series analysis, but as a classical statistical machine learning problem where we engineered features from the data set and we predicted essentially a corrected value for the value that came out of the API. One of the features we engineered, of course, was how old was the prediction, right? When you're 7 days after the time of prediction, your error is going to be bigger than if you're an hour after the prediction. And this was to be done on an hourly basis for 7 days. So we had 148 predictions to do to see what we would get. So we used a technique called gradient boosted trees. So this is a classical machine learning algorithm problem. It's known as an ensemble. Each one of the algorithm is a decision tree. You can see here a decision tree. These are not very powerful algorithm, but if you combine them, if you have 100 decision tree, the combination of these trees actually give you a pretty powerful algorithm. So I knew that for this type of data, this usually works pretty well. And this is our results. What you see here is in blue is the actual correct values, so that we know after the fact, so after the 7 days. And in purple, you have our predictions for all 6 of those parameters. And you can see the 2 curves match pretty well. But But it's much easier to see this in numbers, okay? So here we have the RMSSE, which was the metric that we want to use to compare our model. So the benchmark is effectively the open weather API that we've used, and lower values are better. So for temperatures, relative humidity at 2 locations, you can see that our values are lower than the benchmark values. So we have effectively improved on those predictions. For precipitation and global tilted irradiance, we actually have not improved that much on the open weather. So it still is a very difficult problem to track, but we've also not actually, we've not degraded the performance. So at least that was nice to see when we got the result. And thanks to this, we made top 5 in the competition. But at least that gives you a little flavor of how machine learning can be used in conjunction with API or predictive models to improve or maybe increase the temporal resolution of our models. So now I want to switch to something else, which is remote sensing. So using satellite data, which is very important when you do weather predictions, because you can bring that weather data immediately into your model using data assimilation. But it's also very important for climate monitoring, right? And there are challenges with this as well. So here you see an example, several photos. This is Lizard Island in Australia. And you can see immediately that there are some issues with using satellite data. So one of the issues that satellite data is very large. It's a very, very heavy type of data, and it's not always of good quality, right? It's not always of good quality. So for instance, you could have too much cloud. Now, if you want to predict cloud cover, that's great. But if you want to look at what's below the clouds, that's not great, okay? So that's a challenge that we have. Let's see with this. No, okay. The other issue that we frankly discovered when we tried to do this work is that atmospheric correction is inconsistent, okay? So you get data coming straight from the API from ERA 5, or you get it straight from Sentinel or the different providers, and the image are not corrected in a very consistent manner, and it's often a black box actually. It's very hard to know what it is. Our goal here was to monitor the health of coral reefs, right? We were really interested in understanding how climate change impacts coral reefs. For this, we needed to have very consistent scenes, and we discovered that this was not consistent. So Ziad's PhD became very quickly about improving image correction. And we've also discovered that cloud removal or estimate of cloud cover is not very good out of the box. You know, the F-mask or the algorithm that are used out of the box are not very good. So that's why we worked for about 2 years on trying to improve this, and we have now this done, and it's a paper that's currently submitted and in review. So what was our solution? So this shows you the entire workflow. And what should be immediately apparent is that what we have is a machine learning solution. It's a classical machine learning. It's not a deep learning. It's a statistical machine learning approach. And you can see that we use principal component analysis quite a bit. There are several places here where we use PCA. Why? Because PCA allows us to reorient the data into axes that are perpendicular to each other. So we can immediately see what has the most importance on the variance, but also because it allows us to visualize the most variance of the data by choosing 2 of the component. And thanks to this visualization, we can then separate, it's kind of a dimensionality reduction, we can then separate things into good scene and not so good scene. It'll become apparent when I show you the results. So the first thing we had to do was to find a quick way to be able to select, because we were interested in doing time series to see the evolution of coral reefs, but we wanted good quality time series, okay? So we had to find a quick way to estimate what scene were good and what scene were not good. And using the PCA was very helpful, because you can see here the images, those little tiny dots, so those are just the preview images. They're small. They're not costing a lot of data. And thanks to this, we can immediately see with the PCA if we have increased cloud coverage, if we have poor color balance, or if we have a good scene. So we can select very quickly which scenes are good for any particular point of the globe and only focus on those images that we know are good to download the full data. Then the other problem was the way the image was basically pre-processed. And we found out that essentially we had to apply, because we had a lot of glinting. I mean, one of the difficult things, and this is something in Indonesia should speak to you, one of the difficult things is if you're looking at sea scenes, if you have sea, all of the algorithm that you use for data processing in satellite really are based on land masses, right? So they're based on dark vegetation, dark patches, but if you're looking at corals or sandy beaches or things like this, these algorithms don't work really well. So we found that we could actually reprocess the image by thresholding the image and then essentially obtaining much more consistent imagery in terms of how they look. And ultimately, our goal was to be able to basically look at the different environment of deposition, so be able to classify these different parts of the reef. And for this, we use superpixel, which is a technique that essentially looks at like the similarity between different pixels and puts them together, and then use this as a unsupervised way of classifying the different parts of the reefs. So did it work? I'll let you be the judge. So this is, again, Lizard Island. On the left is the satellite imagery. On the right is Ziad's superpixel estimate. And you can see that the images are pretty consistent. Sometimes you have parts missing. Those are the images where we have cloud cover. And we've admitted 20% cloud cover as acceptable on the island so that we can monitor still parts of the reef. So sometimes we miss part of the image, but we have control on what we take here. So here this gives you an example of how we can use essentially these AI technique to automate the processing, selection, and classification of satellite imagery. And then you do what you want with that image. Either you can monitor climate change or you can use it into weather prediction. And that brings me now to the second part of the talk in terms of the research. And we're going to talk more about the geophysics aspect of this work. So one of the things we're interested in my group is to be able to image the subsurface. Now, we use seismic reflection for this. Don't know if you're very familiar with seismic reflection, but the idea is that you basically create a source of noise at the surface, so that could be an explosion or a vibration, and then you use the time of return of the waves to essentially image the subsurface. Why is this important? There's many reasons why it's important. You might be interested in resources like water, oil and gas. That's classically where it's applied. But you might also be worried about earthquakes, for instance, and you might want to image where the different fractures are, their geometry, and things like this. One of the problems with this technique and what my postdoc, Haifa, is focusing on is that the data that comes back is not always or is rarely completely full. You often have basically lines missing or data missing, okay? What's the impact of that data missing? So here what you see at the top is a profile. So that's a seismic profile. It's a marine profile. And you have 5 different lines, okay? So they're basically from the same seismic survey, but they're different lines. These lines, the second part, what you can see is we have the segmentation. So this is essentially using deep learning algorithms. So now we're using deep learning. We're segmenting the seismic data into different environment of deposition or different facies, right? Different types of rocks, if you want to think of it this way. So the second line is the ground truth. So that's what a human thing is the truth, okay? Then you can see what we did is we actually induced some missing data. That's the third line of this plot. And then we try to segment this with the missing data. And then that's the fourth line. You can see it's absolutely difficult to do this properly, right? Let's see if that works. Oh, yeah, maybe. Okay. Well, it's invisible. This is the missing data. This is the segmentation. This is another type of missing data. And this is the segmentation. So you can see the impact of missing data is tremendous, okay? So the goal of our work here is to use deep learning without supervision to reconstruct the missing data. So for this, we use essentially a design experiment in 2 phases. Again, this is something we've submitted now for publication. So in the first phase, essentially what we do is we reconstruct the data using 2 types of algorithms. So we compare 2 types of algorithm, an autoencoder and a UNet. So these are 2 types of very well-known architectures. And phase 1 is all about reconstructing the data. To know, so we can of course quantify how good the fit is with the original image because we know what the original image is. But to really demonstrate how well this works, we then have a phase 2 where we do the segmentation that I showed you before and we see how well it works. So this is actually our results. So you can see we have different approaches. So I'll break them out for you. So first of all, we use 2 types of equations to assess how well our fit is. One is using the mean squared error, MSE. So all the algorithms that start with M use the mean square error. And then we used, I'll show you in a second, we use the winner loss, which is something that was introduced about 2 years ago and that we're the first ones to use actually in geophysical reconstruction. Then of course we have the 2 types of algorithms, so autoencoder and we also have the UNet. So here I'm showing you the results for the autoencoder. The UNet looks very, very similar. So that's the A here. And then we either have cubes missing or trace missing, so different types of deformation. The bottom line is that in all cases, you can see that if you look at the last example, that's the difference, so essentially the error is minimum when we use the winner loss, okay? So that new winner loss. So the winner loss is based on the winner filter in geophysics, and we think it's superior in this case, or we argue it's superior, because it's actually able to, it's not just looking at a pixel-based difference, it's looking at the difference that is geographically spread throughout the volume of seismic. So it actually is aware of the entire image and not just of its local difference. Again, we can look at numbers. Images only go so far, and the point is with the winner loss, we actually get the best results. We beat all the previous record in this type of application. So the take home here is that we can actually use deep learning in geophysics, in this case seismic reflection, to get much better reconstruction of the data. So if data integrity is a problem or a worry for you, we can do data integrity no matter what your signal is. Think of this as a signal. It could be a very different signal. It could be a weather signal. It could be an instrumental signal. Deep learning is great if you need to do signal processing. And just to, kind of like give you the proof in the pudding, you can see here the different type of reconstructions we have, and you can see they're much better than if we just, the first slide I showed you, where we have the initial data with the missing data. Okay, that's our ground truth, and that's our winner loss, and you can see they're very similar. The MSE loss does okay too, so it's not bad, but winner loss has an edge here. Even though it's not perfect, it definitely works much better. And again, if you look at number for segmentation results, same thing. The winner loss actually does better. What's surprising is it even does better than if you use the original image. So the image without us removing the data still has noise. And if you apply this to images where we're missing data, we get a better segmentation because we also take care of the noise. And that's one of the nice kind of like bonus of using machine learning for this type of application. Now, typically as a geologist, when you produce seismic volume, you're not just interested in completing it. You're also interested in interpreting it. And with my student Walid, that's exactly what we do. What we do is we use deep learning to do the interpretation of the seismic. Okay, but the problem, the challenge with seismic is, and that's something that we geoscientists, earth scientists face a lot, we don't have a lot of data, okay? Even though we have very large data, we don't have a lot of labeled data. So how can we get around this? Well, there are multiple techniques that we can use. The one we decided to use with Walid is simply to focus on synthetic data. So you can create your own data if you don't have data. Of course, that data needs to be close enough from the real thing to be useful. So I'll try to convince you that in this case we succeeded. So we created some very simple model. This is model of the subsurface that you can clearly see is not seismic. Then we apply an acoustic impedance to it. So we choose relevant acoustic impedance. Walid is a geophysicist. He works actually for Saudi Aramco. He's doing his PhD with me now, but he has a lot of experience in this. Then we take a reflection coefficient, again, realistic reflection coefficient. And finally, we can convolve a Ricker wavelet to transform our data into a pseudo-seismic. And this is what we obtain, okay? Here you have a synthetic seismic. The problem is this synthetic seismic is too perfect, okay? So we just add noise. You just add Gaussian noise to it to make it more realistic. And what we obtain is this. So this is all synthetic data. And synthetic data is something we have a lot of experience in my group with different types of data. And it's very, very simple what we're trying to do. We have two classes. One is no reflector termination, so essentially parallel lamination. And one is reflector termination, which I'll show you here in green. And then what we can do with the synthetic data is train a deep learning algorithm, because we can create 1 million synthetic data record. It's very cheap to do, okay? And we then trained an algorithm similar to VGG19. Actually, Walid used his own architecture, but you could train a VGG19 or any deep learning algorithm you want. It doesn't really matter what the architecture is. This is a computer vision algorithm, so it's a little bit more complicated than what I showed you in the first slide. It's a system that is able to basically extract feature from images, okay? But the real question is, does it work, right? That's always the proof in the pudding. So what we did is we used like real seismic data. And essentially what we did is Walid did an interpretation of this seismic data himself. And here, if you're a geologist or a geophysicist, you'll recognize that he's identified faults. So again, if you're interested in earthquake, those could be area of interest. He's also identified terminations. And then we basically use the train algorithm. Remember, train on synthetic seismic. We pass it as a moving window. So we make lots of prediction on this volume. And we average these predictions. For each pixel in the image, we have multiple predictions. And then we build a map of probability of termination. Okay, this is the map of probability of termination that the algorithm gives us. And it highlights in yellow areas where the geophysicists should really spend their time looking, because that's a big problem. The volume of data is such that you don't have the time to look at everything in detail. So this map draws your eye to areas where the algorithm thinks you should be looking. And if I overlap Walid's initial interpretation, you can see that there's a good correspondence between the faults he found, the termination he found, and where the algorithm, trained on synthetic data, found this. So here the lesson is you can actually really build either early warning systems or systems to look at large volume of data using deep learning, even if you use synthetic seismic, and even if you still have a human in the loop, it helps you to make things much faster. So that brings me to another aspect of geophysics, where when you look at the subsurface, it's sometimes looking at logs, okay? So here you see two drilling vessels that recovered rocks from the subsurface. In the middle, you basically have the amount of rock that was recovered. The rock is in black, okay? Here. So you can see, mostly we did not recover the rock, okay? And that's a very, very well-known problem when you drill in the sea, you don't recover the rock. Luckily, we can use geophysics in the form of instrumentation, so we can send probes in the subsurface that measure property on a continuous basis. So now we have a continuous record. The problem with that continuous record, here we're going to focus on a particular type of record called the FMS. Okay, so that's the FMS, the formation microscanner. It's a resistivity image of the subsurface, and it gives you an idea of how the rock looks, okay? But it's not easy to interpret. In fact, will convince you that it's very difficult for geologists to interpret this. Geophysicists that are trained specifically on this type of data will do better, but even for them it's very difficult to do so, and it's impossible to really interpret this at the small scale. You need to look at the much larger scale if you're interested in this. So, because it's hard to interpret, the question we asked with my other student, Saira Baharudin, she's Malaysian, was whether or not we could actually transform this into a synthetic image of a core or a synthetic image of a rock. So can we use generative AI like ChatGPT, okay, to basically transform this orange image into the image on the right? Okay, so generative AI is a big, big, big topic now, and we are interested in using it for science purposes. So to make a long story short, because this was 2.5 years of work, and I don't have 2.5 years to tell you about it, we used an architecture known as a GAN, or Generative Adversarial Network. It's a relatively old architecture, but that works really well in a supervised manner. So we used Pix2Pix HD, for those of you who are really geeky and want to Google what we did. And we found the best way to treat the data. So data science is very important. So understanding your data, treating your data is super important. Then we train an algorithm to generate the pseudo cores. So did it work? Well, okay, I'll let you be the judges. Okay, so here are 3 cores, and under the yellow arrow you have the real rocks. Okay, these are real rock images. Under the blue arrow, these are fake rocks. These are synthetic AI-generated rock for the same interval based on the FMS data. And it looks very similar, okay? You will notice, if you're not geologists, you may not know this, but the 2 first ones, so the one on your left and the one in the middle, are relatively fine-grained rocks, and they look like the statistical distribution of the rock generated looks very good. The one on the right is much coarser. You can see there's large blocks. Those are essentially they're rhodolites, but think of them as coral fragments if you want. And you can see those are actually not super well visible in a coarser rock. Why is this? Well, because the trick is what we generate are smaller images, smaller patches, as you can see here, and we put these smaller patches together. So that's one of the limitations of the approach. But the real question is, does it make a difference, okay? And so we're going to test this, and I had my research group to use to test this method. So what I'm going to show you is a very simple exercise. We're going to give my research group some images of the rock. Okay, so this is the actual real rock. And we're going to ask them to tell us what texture, Dunham texture, which is a way of classifying the rock, and we're going to ask them to classify this rock. And this is their result. So this is a confusion matrix, okay? So let me explain what a confusion matrix is so that it's clear to everybody. So essentially, a confusion matrix is a double entry table. On the vertical axis here, you have the actual label of the rock. So this is the real class of the rock. On the horizontal axis, what you have is the predicted label. So that's what the algorithm, in this case humans, right? But if it was an AI algorithm, that's what it would tell us. But this is human classification. So that's what my research group think the class is, okay? And inside the confusion matrix, you have the proportion of classification that falls in each one of those grids. So what it actually is and what people think it is. And the very important thing is this diagonal here, okay? The diagonal is where it's the only place on this matrix where the actual label and the predicted label are the same. So in other words, those are correct prediction. We represent this as a heat map. So the darker the blue, the more samples fall on that particular box. And you can see my group is pretty good at predicting the Dunham texture from actual rocks, okay? No problem there. They get about 87% accuracy, so they make very little mistakes. So now we're going to do something fun. We're going to give them the FMS data. And that's how it looks, okay? That's the same scale FMS data. I'll be honest with you guys, I cannot interpret this, right? I have no idea what the texture of this is, and judging by the results, neither can my research group, okay? Look at the average accuracy on this data, it's 14%. Because we have 5 classes, that's essentially a random guess. You can see we don't have this nice diagonal, so essentially if you just give them at the same scale FMS data, humans are not able to interpret it. So now, of course, is the interesting thing. What if we took that FMS data, we pass it through our train algorithm, this is data that was not seen at train time, and generate a synthetic image, and then give this to the humans, my research group, and ask them to do the classification. Well then, we're back to something usable, okay? With synthetic data based off FMS data, the group is able to get a 73% accuracy, which is not as good as with the real thing, but way, 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 way better than with the FMS data. So you can see here how the generative AI technology can really be a help for this type of approach. What's even better is we know where the source of error is. If you look at where we make most of the error on this confusion matrix, it's essentially large textures that human interpret as much less coarse. And we know that this is because our current algorithm is not doing a good job at reproducing the coarse texture, and I have a postdoc working on this at the moment. So we think we have ways around this. Okay, last example, and maybe one of the most relevant for you guys. We also are interested in predicting earthquakes, okay? So this is directly of relevance to Indonesia, where there's a lot of earthquakes. Specifically what we did, this was an MSc project, so if you guys do a master's project, this is the sort of thing you could work in. We've submitted this to geology for publication, so we've just literally yesterday submitted the second version of the paper. So here what you see is all the subduction margins around the Pacific, and there was a paper that was published with 5 different type of feature for these subduction zones. So some of it was sediment thickness, some of it was spreading rate, but only 5 features. And we were very curious to see if we could actually predict areas that don't have large earthquake, that are slow slip events, but where maybe a large earthquake is possible. So for this, I'll go relatively quickly, but we did something, which is we took the data in its original form, so the features themselves, and we transformed them using PCA, different versions of PCA. So that's how it looks, okay? So again, PCA, principal component analysis, it's essentially a mathematical way of reorienting the axes of our data. So because we have 5 features, we have 5 axes, and I show you here PC1 and PC2. PC1 has the most variance of the data, PC2 the second most variance of the data. And then at the top, I show you the different region that we looked. Actually, Sumatra here is at the top, so hey, very local. And at the bottom, I show you those same areas classified by magnitude, average magnitude of earthquakes, okay? So we obtain a map, you see in the middle, a map of density where most of these big earthquakes are and where less of the big earthquakes are. And then we can interrogate this map, because the problem with earthquakes is if you have frequent earthquake, we know they're there, okay? But what if you have a relatively slow subduction zone where maybe we have one massive earthquake every 100, 150 years or more? Then we don't have a record to predict this. We argue this, that if you look at our map, our PCA map, we can then plot areas that do not have recorded earthquakes, and we can look here, you can see the color shows you magnitude 8 earthquakes, larger than 8.5 earthquakes, and you can see what's really interesting is some of those margin who have not had large earthquakes have similar characteristic than other margin where large earthquake occurred. So that's, for instance, the case with the Hikurangi margin. It's also the case with the Cascadia margin. So we argue, because they fall into this red zone, we argue that this is areas where you have to be very careful about the reoccurrence of very, very large magnitude earthquake over hundreds of years, okay? So that's a way of essentially getting not an early warning system, but at least some knowledge about what is potentially a zone of danger. Okay, so I've covered a lot. There's a lot that I do in my research, so briefly on this slide, I'll mention them. So I do a lot of work on forward modeling, and I use a lot of the technique from weather prediction in forward modeling. I also work on Mars and remote sensing on Mars. So I have a student looking at hyperspectral imaging and AI to denoise the image and then automatically classify every pixel for main mineralogy. I use a lot of AI for geological core analysis. And I also work on computer vision to detect different types of organisms. For instance, we have a published paper on the Great Barrier Reef. These are maybe topics of lesser interest to the BMKG. That's why I didn't really focus on them today. But we have a pretty broad area of research interest. So you might be relieved to know that I'm reaching my conclusions. So very briefly, I think AI, the type of research I do, but also the tool itself, AI is very flexible. So we can do a lot of different applications. So if you have an idea and you're interested in an MSc or a PhD, but it's not covered by what I showed, don't be shy, come and talk to me. We can decide if, what would be possible, how it works. I have deep expertise in earth science, so I've spent more than 20 years working in this field, and I'm very multidisciplinary, so I'm interested in a lot of different aspects. And I think that AI has a very, very big role to play, and we're just at the beginning of seeing how we can use AI for geospatial problems. As earth scientists, whether you're interested in climate, weather, meteorology, or earth science in general, essentially we look at things that have a time component and a geospatial component, okay? And AI in this sphere is a little bit more complicated, but luckily we understand what we're doing, and I think it has a lot of potential. And if you're young, I think it's a very exciting field, and I also think it's a field that, in terms of like your career, having some knowledge of it, even if you're not an expert in it or becoming even an expert, I think it's something that will help you in your career. And I think we really have like some exciting years ahead of us. So last slide, just to say thank you to you, but also to the different MSc, PhD, and postdoc who have worked with me. So I've put here some of the MSc and PhD and postdoc that have contributed either directly or indirectly to this talk. And I want to mention 2 PhDs that actually have done nothing with AI. They've worked with me on geochemistry, but they're Indonesian, and they both came with LPDP. So if you ever want to work with me and you need to talk to an Indonesian PhD, they gave me the green light to send their email so you can talk to them. Ki is back in Bandung. He works for BRIN, and Adipa is in Saudi. He's now a research associate there, but both came with LPDP funding. And I thank you for your attention, and if we have time, I'd love to take questions. Thank you.
Okay, thank you very much for very interesting and this is very hook topic maybe. And so please, we now open the discussion and question. So please feel free and please state your name and program. Maybe this is big opportunity for you to ask question, especially for the student with the final task in machine learning or AI. Okay, please.
Don't be shy.
Don't be shy. Okay, maybe I think it's directly.
Thank you for the opportunity. I feel honorable to be able to ask the question to Mr. Cedric. Let me introduce myself. My name is Michael Smangsong. You can call me Michael. And my question is, actually I'm on my ongoing research now is about the self-supervised learning, that same task in natural language processing and in the image processing also. And it's for the weather prediction. And as I can see, it's the AI. It's so big. Like the structure is big, and we have some of like the threshold and extract equation, and it's so hard to me to understanding, especially in self-supervised learning. And for and we know, and my ongoing research is likely in Indonesia, and it's a tropical, yes, field, and it's like the atmospheric dynamic is so wild. And if I see the many research, they do the same research, but it's in mid latitude, and I don't feel like it's it's make me kind of anxious, like how this is possibly work if I go on there.
Uh-huh.
And the second question is, I see the what the AI do the things is very smoothly, like in the geophysics. And why do we have to make the downstream, like make the noise? It's like not make sense to me. When you say it's too smooth and you make some noise to the picture, to the pixel, how is it works, and how we that is is it make is it not make sense, right? Like it's actually a good, it's smooth, but why do we make some noise to the picture?
Yeah.
Thank you.
All right, thank you very much. Very, very good questions. So I'll start answering your second question. And I totally understand why it's confusing. You have to realize when you make synthetic data, your goal is not to make perfect data. Your goal is to make data that looks real, because you're going to use this data to train your algorithm. Real data always has noise. Real data is never perfect. That's why we add noise to emulate the real seismic data. If we were to use perfect data, it'd be very easy to train the algorithm, or easier, but then when we apply it to real data, it would not work well, because the real data has a different statistical distribution because of the noise. So hopefully that answers and clarifies why we added noise, but yeah, I realize I didn't explain this very clearly. So, good? Yes? Okay, great. Okay, now your second question, yes, so large language model or large models, and the fact that we work, that we're in a tropical climate. So first of all, I can confirm we are in a tropical climate. That became apparent when I stepped out of the plane, because in London it's now 5 degrees Celsius. So, so yes, and you're absolutely correct that the dynamic is completely different. And you're right to worry about how applicable things are when you compare what is done in the northern hemisphere compared to what you do in the tropics. So you're absolutely, you're spot on. Your instinct is spot on. You have to be worried about not using things that are trained in the north or the south at high latitude in your particular region, if these are regional climate models, because they will not work. And one of the really important things with machine learning is to understand that you need to have training data. Again, we go back to this same principle. You have to have training data that is similar to your application data, okay? So if you have something that is trained just on the high latitude and you apply it to the dynamic of the atmosphere in the tropics, it will absolutely not work. That's not to say that if you have your own data and you train with tropical physics, with the physics of the tropics in terms of the atmosphere's physics, you should be able to train your algorithm to work very well. So I wouldn't be too worried about it. Now, what you're doing is large language models, right? You're using large language models and computer vision. So you're brave. You're jumping right into the deep end, and it's normal that you don't understand it. I'll be honest, because you start with things that are very complicated, like transformers, vision transformers, or transformers for large language models. They're extremely complicated architecture to understand, just because they're at the top of what 40 years of research in machine learning and deep learning has produced, right? So don't feel that you should understand everything. I think it comes with time. If you decide to do a PhD or a master's, you'll have more time to understand those architectures maybe more deeply. If you're worried about not understanding how your model makes a decision, so if you're worried about how transparent your model is, that's also a valid concern. This is something that is an area of research, essentially interpretable or explainable AI, if you've heard the term. And one of the problems with very large model like transformers is we don't really understand how the model goes from input to output. And that's one of the limitations of those very large models, right? When you have a full physics model, you understand the equations that go in, you understand how, you may not understand what you don't know, you may not understand truly the distribution of your error, but at least you understand the physics, right? So the error is linked to the error in your physics or the boundary condition. With large models, sometimes you can have hallucination, if you heard the term, right? Where essentially ChatGPT, as an example, will give you things that don't exist, right? But it will be very convincing in giving you those things. So that's another thing. My advice to you is understand the basics of machine learning, understand the statistical machine learning algorithm, because they're much easier and they're based on the same principle. So if you understand those well, it will allow you then to build your understanding to the larger models. If interpretability is a very important goal to you, then you also have to think about using simpler model than the large language models. So sometimes we don't care. Sometimes a black box, as long as we can prove that it works, okay? And that's where those large models are really useful. But if you're like an insurance company, you need to be able to demonstrate why your decision is based on data, on facts. Then you need some form of interpretability. Then there are ways around this. A lot of them don't involve large language models. Does that answer your question? Yes? Okay, good.
Okay, thank you. Okay, next, another question for audience. Oke, silakan Pak Dodo, Mr. Dodo.
Thank you, John. Very interesting talks. I'm a climatologist, so the part one that I entered on. This is about can any algorithm on AI replacing the tool or observation instruments. Yeah, so in the future, maybe once, I'm coming from BMKJ, so
Yes.
understanding about the instruments, say automatic weather station. This electronic instrument, of course, after 5 years, maybe stop maintaining very expensive.
Yeah.
So can once we have 5 years data of this automatic weather station, and for the continuing it replacing by the AI.
Okay.
That's what.
Yeah. Okay. Great question. The answer is you're not gonna like the answer. No, because it's two different things. Okay. So you're talking about the instrumentation, which is getting the data. So when you look at the way we use AI today in weather prediction, we still do data assimilation, data fusion from the weather station into the model. And I don't see a future where you stop doing this. And the reason for this is climate change. If you had a system that was completely predictable, it would be easy, okay? Then you don't need to actually measure the data because your baseline stays the same. There's no change in the weather pattern. We understand it fully well. We've fully characterized it. We don't need to measure data anymore at all, okay? We can predict forever what the weather pattern will be. But of course, this is not the case. First of all, the physics of weather is so non-linear and complex that, the butterfly effect, right? That we can't really predict on long horizons, right? Even 7-day prediction is difficult today, right? The second problem is your baseline is changing, right? So you have weather prediction, but you also have climate change. So the conditions are changing. So if you train an algorithm today on data from today and you apply it in 10 years, I don't think it will work very well. So it's not a thing that you sort once and then forget and use forever in the future. You can sort once on the physics, so you understand the physics very well. So you can train a surrogate model based on the outcome or the output of a broad range of input data from your full physics model. So then you get kind of a general approximator of your full physics model, something that's very quick, snappy to do the computation. So that's what's done today. So maybe you can do that and not worry about retraining this. But this still requires the boundary condition, and what gives you the boundary condition is the data that you measure at the weather station. So I'm a data guy, right? I come from also instrumentation, I come from observation, and I really don't see like the algorithm living on its own. I think data and algorithm are two pieces of the same coin. So you'll still need the weather station and the investment in the weather station, yeah. Maybe we can get away with less observation if the algorithm become better, if we understand these things better. Maybe we'll be able to determine where we really need the observation, and maybe we can reduce this, so we can reduce the cost. So there are ways where we can reduce that cost, but I don't see this disappearing. Is that a bad news or a good news for you?
Yes, as you mentioned also, because data is sort of not so, yeah, observation is not so much.
Yes, yes, there is a lot of data, yes.
There is no data in this particular area.
Yes, so you're right. And like it's very, the data observation is sparse, and it's not actually. You have areas where you have dense observation and areas where you have no observation, right? And if you look at historical record, it's even worse, right? So we're getting better data, but in the past, if you want to train over 10 years, 20 years, you don't have that much data actually in some areas. So yeah, that's a problem. But I also think it's an interesting problem. I think it's something where, all these machine learning AI is data-based. It's basically data modeling, so we need the data. But we can probably become more clever about what data we need, where we need it, and be more systematic. And I think there's going to be also some very regional problems. What are you trying to predict, right? What is the thing you really want to know? Okay, is it precipitation? Is it drought? Is it like extreme weather events, for instance, like storm and things like this? And for this problem, what data do you need, and where is the critical observation? I don't think that there is answer to this question today on very specific local problems.
Thank you, Mr. Dodo. Okay, Mr. Rista, please.
Okay, good afternoon. Nice to meet you. I'm Mr. Hernandi, lecturer from climatology program. I have two questions for you. The first one is, in your opinion, what are the biggest challenges in the future in doing research about using AI in geosciences?
Mm-hmm.
And then how do we do to overcome those challenges? And then the second question is, we know that most of AI models are being data-driven, so it's specialized for its training data sets. And how do we do to ensure the biases that comes from the data training period not to distort our analysis and the conclusion in our research? Thank you.
Yeah, thanks. Those are great questions. And actually, I think they're quite linked, those two questions. So I think right now the greatest challenge is precisely what you ask in your second question, which is it's relatively easy, say, to train a model with a given grid to reproduce, to understand, say, around Java, right? To reproduce the weather around Java. The problem is this trained model on that particular grid will always need the same grid, the same dimension, and will only work in Java. So how do you apply this to Sumatra? Well, you have to retrain another model, right? And so that's a bit of an issue because we're data-driven, and when you look at modeling, because we essentially, when we approach modeling from a deep learning perspective, often we treat this as a computer vision problem, and each grid becomes a pixel. Then it's easy, you reproduce, the pixel is basically a property, whatever the property is you want to do. But that limits how much we can actually apply this to other region. What is the solution? Well, the solution is to develop algorithms that are not so tied to the grid, okay? And one of the things we are exploring right now is the so-called physics-driven machine learning. In physics-driven machine learning, you're not trying to predict something on a grid, you're trying to basically create a universal PDE, partial differential equation solver, that looks not just at the data, but also looks at the principle of the physics equation behind the data. So in other words, if you're familiar with machine learning or deep learning, we have what is known as the loss function. The loss function is how we calculate the error the model makes at training, during training time. So in physics-driven machine learning, what you do is you have a loss that is data driven, so that's your data loss, and then you have a physics loss, which is essentially a PDE solver. Now, physics or PINs, physics-informed neural networks, is kind of a new topic. They're known to be quite difficult to train. They've shown great success in some, for instance, fluid computation, fluid dynamic computation. They've shown great success, but they've also been known to be hard to train, and they're extremely slow to train because you essentially have to run your full PDE solver each time at each epoch of training. So that's a challenge. So computation cost and architecture and also just the whole principle of how do you train a pins is really kind of like cutting edge research right now. So maybe in 5 years, you know, I'll have a different perspective on it, but at the moment I think it's very exciting because they're grid free. They basically take you out of the grid problems and then you model whatever you want. So we're gonna try to use this. So that's the answer to your first question. Your second question is, yeah, you're absolutely right. Like, how do we get around the bias of our data? The truth is you don't, okay? So, and that's, you have to realize that when you train with data, you have inherent bias in your data. So what you need to do as a data scientist is two things. First, you need to make sure that your bias is not conscious. So you try to give the data that is as unbiased as possible. So not, for instance, again, we talked about, you know, where you have your observations. If all of your observations are in Jakarta, that's a big bias for the rest of the country, right? So everything's going to be based on Jakarta in terms of the observations. So you can try to handle this. But the biggest thing and the biggest problem I see in papers in earth sciences that I have to review is how when you train a machine learning algorithm, you have to assess its error, right? That's how you know how it performs, okay? To do this, you need to have what is known as a test set. Okay, a test set is essentially data you don't use for your training, and then you evaluate on your train model on that test set, and then you know in the wild, so when you deploy it, what the error should be that your model is doing. And you have really two big ways to prepare a test set. One is basically known as random sampling. So if you have 1,000 examples, you keep 20%, so you keep 200 examples randomly in your data set to assess how your algorithm works. This is the most used method, and it works very well for many problems, okay? And it's very simple to do. Then you have another way to do it, which is geographic splitting. So if you have a geographic problem, which every earth science problem in the world is, including weather, what you want to do is you want to separate a region of your data as your test set. Why do you want to do this? Well, it's because what you're going to do is you're going to predict things on unknown region in the future. So you want to see how your algorithm performs on unknown region. If you randomly split, we have what is known as geographic covariance. So a data point here and a data point here will be more similar than this data point and that data point, just because it's further away, so different conditions. So if you randomly split, you have bias through data leakage, because you get false confidence that you make very good prediction, but that's because your train set and your test set is too similar, okay? And when you apply it then, again, to take my simple example from Java to Sumatra, well, you're gonna think that you have a 10% error rate when in fact you have a 15 or 20% error rate. So you're gonna be overconfident in applying your algorithm. So that's one way where you can, you know, manage your bias, and I think it's a very important thing. You're welcome.
Thank you very much. We give a close. Okay. Maybe the time is over. We must closing the discussion. Okay.
Thank you.
Ladies and gentlemen, we have to the end of today's lecture. On behalf of STMKG, I would like to extend our deepest appreciation to Professor Kedri John for sharing his experience with us. Please give applause again. And then, yeah, your insight into the application of AI in weather, climate, and geophysics have truly enrich our understanding of this critical field. Would also like to all participants, thanks to all participants for your enthusiasm and active participation during today's session. And then as we conclude, let's us remember that the vital importance of today's discussion, the integration of AI in weather, climate, and geophysical science is not just an academic pursuit. It is necessity for like a building of safer, more resilient future. Yeah, your role of future expert is pivotal, and we hope this lecture has sparked idea and inspiration for your journey ahead. With that, we officially close today for the general lecture. Please give applause again for all with us. And have a wonderful ahead. Thank you very much.
Thank you very much. Thank you for the invitation as well. It was a
Okay,
pleasure.
thank you.
Thank you, Mr. Benjamin Herianto Santo and Mr. Cedric John, for the insightful session and for sharing your valuable insight with us. Let us give another round of applause. Before we proceed to the next agenda, we would like to take a moment for documentation purpose. I kindly request the present two speaker, Vice Director of STMKG, the moderator, and all the lecturers for a documentation. Just stays in place and our team will take the documentation from the stage. We honor all the lecturers closer to the middle. And I invite all the participants to stand. Okay. 1, 2, 3. 1, 2, 3. Thank you, and I invite to sit back. Thank you for your kind cooperation during these documentation sessions. We truly appreciate your participation. Excellencies, participants, ladies and gentlemen, that's a wrap for this general lecture. Thank you for joining us for this insightful lecture. Your engagement has enriched our gathering. Take the inspiration with you and apply the knowledge gained. We appreciate your time and attention during this session. On behalf of our committee, I would like to apologize for any mistakes that have may occur. Wassalamualaikum warahmatullahi wabarakatuh. Good morning, thank you, and we look forward to further collaboration with you in the future events. Thank you very much.